Hi guys, welcome to Learn Electronics Repair. It's that time of year again. So every year the Christmas lights, these are the outdoor ones we have, get put away, and then the next year they're not working. There's always something broken. So I have 3 sets here at least, maybe 4 sets I need to have a look at. But normally these things are fairly easy to fix and they can be a bit expensive. So let's see what we can do with them. This is the first ones we actually looked at. These last year. We actually reverse engineered this and figured out how these actually work, because we have a 8-pin chip on here. That one, but there's like 20 lights in the sequence, and we reverse engineered it and worked out how you can control so many lights individually, LEDs from 8 pins. Yeah, you can see these have been used for years, a bit rusty, but this was from the UK. It doesn't really rain here. Having said that, it rained last night. We had a thunderstorm. That's the first time I've seen rain here since probably August last year. No, maybe we had one time in the winter as well when we had some rain, but very rare here. So these things now live on, and each year just need a bit of attention. So you can see what's happened with these. Somehow or other, all this lot are not working. These are working. This one's broken off. I see something else over here that's broken from something as well. So we just need to figure out how to get these working. These are quite simple. You have a 5-volt supply coming in, and I just need to figure out which wires here go where on this one. So let's get a simple one done, and then we'll look at some other ones, and we'll also have a look at the controllers on these Christmas lights, how they work. Can you repair them? Yeah, let's have a look. A bit more reverse engineering to come. So here's a simple one. We have 4 wires here. They actually connect in pairs onto the end of this. So we have the power coming in and then power going out to the next one in the sequence. So we need to figure out which wire is which basically here. So I'm going to do this with the multimeter, of course, on volts range. I have 2 whitish ones and 2 like clear ones. I'm assuming the whitish ones are coming in and the clear ones are going out. I think there's, looking at the wire itself, the wires are the same colour, but this appears to be a different colour from that for whatever reason. So let's look at these 2 white ones and see which polarity, if anything, we have here. And we have 5 volts with the red lead onto the positives. This is the positive end. This is the negative. So I need to figure out now which was the positive going on here. The easiest way is to just have a look at another one and see which way round the wires go. So let's see. A lot of these have been opened before and taped back up. Yeah, this one. Okay, so this is a working one. Which side is the positive? Let's have a look. Yeah, the one on the left hand side is positive, so we know where to put the positive wire coming in. Obviously the one is the negative, and now I need to figure out which of the other 2 wires, which goes to the next one in the sequence, is the positive. Okay, that's this one. Just take this bit of plastic sleeve off. I can put some tape on afterwards. Okay. It should come out. A bit stiff, this one, actually. Yeah, I got it. So which side is the positive lead coming into here? Well, we know it's the right hand one. This is very corroded, but I think we have a connection. And I need to figure out which of the other wires is the positive. In fact, I think I'm going to go for the negative. It's easier to get a connection, I think. So which is the negative? Ohms range or continuity? That's the negative. So I know which the negative is going out. I know which is the positive coming in. So let's solder these. When you're soldering old outdoor use wiring like this, flux is definitely going to help a lot. So let's flux onto it. negative. And the other two, well, actually one of these is very short. Just try and get a connection onto it. I think I might have it. Let's see. So, if I've got it right, all the rest should start to light up now. Yeah, look. Yeah. So I've definitely got a good connection on there. So we need to solder those two onto here. And we know this end is the positive. Again, flux. A fresh solder. Positive. Negative. Does it work? Yes. Okay, so that's that one fixed, and I've probably got them all working now. Of course, I need to find the plastic tube for this. It's probably lost amongst the rest of these, or in the box, which is still at the house. Yeah, getting there with these. This one has just literally fell off, but the wires are actually connected together, so the ones further down the line are actually working. So I'll just solder this one on. I've measured the polarity, so I know what it is. Okay, see. No, it's not working. I've got the polarity the wrong way. Could have. Just double check that. Volts. Yeah, they're all working up to there. Just the negative end. This is the negative side. I think I did have, this is the negative end, okay. So the positive end. Yeah, that one. Okay, give it a go. Yep, that's working on the ones further down the line are working, so yep. Well, almost there as far as this one, and then the last four are not working. So almost certainly what's happened is the wire that goes from this one to the next ones on one end or the other has come off. You can see these have been taped up, so these have been repaired before. So I think one more quick bit of soldering will have these all working. I also found the plastic tube for the other one as well. This is just like, look, which end is the broken connection? Could be either end, so let's have a look. Well, it ain't this end. Yeah, it ain't this end, I'm sure. That looks okay. Or is it? Let's have a look. So, yeah, they are soldered. These are soldered. Must be the other one. So the next one. Typically, when it's 50-50, it never seems to be 50-50 if you get it right or wrong. It's much more often wrong. Yeah, let's have a look. Well, that looks okay as well. So let's just check this with the multimeter. So this is the last one that actually works, and these four don't work. Okay. So we know for sure we have supply getting as far as this one. Okay. And I'm assuming I've seen no voltage here. Correct. So we must have a broken wire somewhere. I'm thinking this looks particularly corroded. That's freshly soldered from a previous repair, but is this wire attached? Let's have a look. So that is soldered down, but we seem to have a bit of wire sticking up here. No, I think that's just a strand of wire. Yeah, it looks like the whole thing is soldered down there. So this corroded looking one, I'm going to add some flux and try resoldering this and see what happens. You're very unlikely to be able to do this sort of soldering without flux, by the way. Okay. Right, let's see. No. Okay. Still none of the last four working. Okay. Resolder this end. It seems to be soldered okay. Bit messy, but it seems to be soldered okay. Ah, I think the problem might be here. Okay. Let's see. No, so we only seem to have power as far as this one. Right, we need to investigate this a little bit. Oh, there's a problem underneath. Yeah, there's the problem. Okay, let's fix that. Now what do we have? Yep, we're almost there. So this one's working. The next one's working. Bit dim, but it's working. Maybe a couple of LEDs out on it, but it works. And then, yeah, this one's working, but it's intermittent. No, it's actually, yeah, this one's intermittent. I'm just waggling the wire on the end, it's gone off again. So it looks like we have one more bad connection here. Go to the last one. Okay, because that one is still working. Well, actually, now I've taped those other two up, they're all working, so I'm not going to mess around with them. So, yeah, just 3 bad soldered joints, the whole lot's working again from practically none of them working. You'd be crazy to throw these things away. I mean, that's like 30 minutes of your time. It'd take you longer to go down the shop to buy some more, yeah? And not only that, because I didn't go and buy some more, I can still go to the shop and add to my Christmas lights. So this year I have even more than last year. Okay, so they are fixed. Let's look at the other set. I have 2 sets of these. I bought them quite a few years ago, prior to 2016 when I left the UK, maybe around 2012 or 2014. I still have these. I've fixed them a couple of times before. These were quite expensive actually. So these do like a waterfall effect. You can only really see it when they're actually out in the line. There's 3 of them, yeah. Maybe get the idea now. So these hang down from the house. They look great. There's a few LEDs or sets of them not working on these. So these things, and generally speaking, most LED Christmas lights work on 24 volts AC. Now you might wonder why they work on AC rather than DC, because, you know, LEDs are DC, yeah? But we can clearly see 24 volt, there's an AC sign, 25 VA, so this is about 1 amp. And on the controller again, 24 volts AC. So why do they run on AC? Well, let's have a look inside this one, because I've opened this before, I repaired it, but before I had the channel actually, so you haven't seen this. So let's have a look to see what we have in here. So this is what's on here, okay? We can see a bridge rectifier on this one, IFPZWWSE, so these are power transistors. Okay, these are the driver transistors, and this is what's switching the LEDs. Now this one's quite unusual because this one actually has a bridge rectifier converting to DC. Usually they don't have, so let me show you how these things are usually working. This is the controller chip. You can see corrosion on this one. Again, this is when it was used in the UK with the bad weather. So this is effectively like a microcontroller that switches these in sequence and effectively controls the LEDs on and off. Now, you can see what was wrong with this with various corrosion. I've resoldered various things. And this one is working. You just saw. It's just literally that probably 1 or 2 of the LEDs have got bad connections like we had on the previous one. I don't recognise this chip actually, EM78P153S. We can have a quick look. And here we have the datasheet for this chip. It's an 8-bit microcontroller with OTP ROM. That's one-time programmable. So once it's programmed, it's programmed. And we have plenty of information on this chip. If we were so inclined, we could get these chips. They're easily available, I've noticed. We could program these. We could even repair this thing if it had a faulty microcontroller by programming another, putting our own sequence into it, get it to do whatever we wanted to do. If we were so inclined, we could do that actually. So there's nothing on this unit we couldn't actually repair. But we could even do that if we didn't have a datasheet like this. Because we can see the way this is built, we can see the 4 resistors drive these transistors, which then drive these transistors and drive the LEDs. That's obvious, I would say, just by looking at this. And we can see that these 4 resistors come back to this microcontroller, which is what is generating the flashing sequence. These 2 have been replaced. You can see that. That's what was wrong with this. Originally, they sort of rotted through, so I fitted some new resistors in there. But without a datasheet, if you had something like this and you wanted to resurrect this, you could program a naked microprocessor, as Detlef likes to call them. You could use one of his little ESP chips or something. You could write a program to do fancy sequences with 2 or 4 sets of lights. In fact, once you've written it, you've got that. And you could replace these things. You could actually stick your own little microcontroller in here with a voltage regulator if it isn't running at the voltage you want, which this probably is actually running at a low voltage, I would imagine. But honestly, guys, you could do what you wanted with these things. You can make your own little controller boards if you wanted and just use the lights, yeah. So any of this stuff is actually fixable. If you're doing a bit of work once, or maybe somebody does it for you, these would be so easy to repair, any of them. But in our case, we know the controller is okay. There is something else wrong with it. We will take a look. But first, I just want to mention why a lot of these units actually run on AC and don't have the bridge rectifier. The reason they usually use AC on these LED light sets is because it's easier to control the LEDs that way. In particular, it's easier to dim them, pulse width modulation. Now, normally with pulse width modulation, you would have a controller, microcontroller, driving, as we saw, some sort of transistor or MOSFET. Okay, we can use a MOSFET to ground, and we would put our load here, so we can have here our chain of some LEDs. Yeah, on the 24 volt supply, there's normally 8 LEDs in the chain. 24 volts. There'll be a resistor somewhere in the chain as well. Okay, usually could just use pulse width modulation, but usually there's a resistor there as well. Microcontroller. And if we want to turn the LEDs on, we just put a high on here, turns the MOSFET on, it turns them on. If we want to turn them off, we put a low here, turns the MOSFET off, turns the LEDs off. If we want to dim them, then we use pulse width modulation. So if we send narrow pulses, the LEDs will be dim. And if we widen the pulses, they'll get brighter until the point we have very wide pulses, or they're just on at full brightness, and that's how we control the brightness. But in this case, the microcontroller has to pulse these effectively fast, very quickly, okay, and it has to control the width of the pulses. So the microcontroller is doing quite a bit of work, and it's especially if it's got 2 or 4 chains of lights on the set. Okay, so the cheap and nasty way to do this, but it's not particularly nasty, is to have your microcontroller. We still have our LEDs, so we have 24 volts AC. This quite often is actually rectified through some rectifier diodes to give us rectified AC. It's not smoothed with capacitors, so we end up with, instead of the AC waveform at 50 Hertz, we end up with full wave rectified at 100 Hertz. So basically the rectifier diodes turn this off of the waveform upside down, so it's positive going, and we end up with this shape of waveform. They'll use one or the other to do this. I wouldn't be surprised cheap ones are just using AC, because LEDs only conduct one way anyway. So what we now have is our resistor, our chain of LEDs, okay, our switching device, but we don't use a MOSFET or a transistor. What we use is a thyristor, silicon controlled rectifier. Okay, like so. And this is your ground, or rather your other end of the AC, because there's no ground on these normally, but this is the other end of your AC. So what the microcontroller now does, it controls the thyristor. When you put a DC voltage on here, it will turn on, and it will stay turned on in 2 conditions. 1, for as long as the DC voltage is there, and 2, for as long as the AC waveform, or this pulse DC, is above 0. When this crosses 0 or reaches 0 and the current flowing through here is 0, this switch is off again. Okay, if the DC is still present, as soon as the cycle starts again, it will switch back on. So effectively, while you maintain the voltage on there, this just stays switched on, and these are at full brightness. Or they could be flickering 50 times a second, depending, how they did it. So you probably might not notice the 50 Hertz flicker, by the way, because the LED itself takes a little bit of time to kind of like light and go out. So when they're using AC, you don't really see that flicker, by the way. That's why they often just do it the cheap way, yeah. Now, what this means is we can do some clever tricks with our microcontroller. So the microcontroller itself will have a DC supply. So somewhere in our controller will be a rectifier, diode or a bridge rectifier going to a capacitor. Okay, probably some sort of resistor or voltage regulator to put the voltage on there that we want. Okay. The microcontroller runs on DC, and the microcontroller will also have a connection to the AC line, and this is monitoring what happens on this line. Okay, so the microcontroller knows when the waveform passes 0. Okay, so what it can do is, if it wants to put these LEDs on full brightness, as soon as the waveform going positive passes 0, it puts a DC voltage on here, or even just a pulse. Once it puts a pulse on here, this will stay switched on until the waveform reaches 0 again. It will switch off. So it doesn't have to worry about it switching off. It just puts one pulse on here, and the thing will stay on for as long as the cycle is above 0. If we want the LEDs on as half brightness, what we do is we wait until the voltage here is the peak of the waveform. It's monitoring it, and it sends this pulse when the voltage here reaches the peak. So at this point in the waveform here, it sends a pulse to the thyristor, or SCR. Okay, same thing. The thyristor now turns on at this point, and it will stay turned on until the waveform passes 0, and it'll switch off again. So again, the microcontroller doesn't have to switch the LEDs back off. They will switch off on their own at that point. And if we then detect the next time this is at the peak, and we send another pulse here, again they'll turn off this half cycle. So you can see that by altering the position of this pulse, we can alter the brightness of the LEDs without having to worry about when to switch them off again. It's a kind of pulse width modulation, effectively. And that's why these light sets have an AC supply, because you can't do this with a DC supply. You would have to use proper PWM. And that's more expensive or more difficult to implement. That's the top and bottom of it. So that's why it works this way. And now I've just noticed I called this a thyristor. There you are. Well, let's look. So the LEDs run in 3 chains on these. We have this one. And we have a few LEDs not working. I can see now as I'm going down here. So in the case of our lights, these, I've just noticed, I've had a look that 2 of these strings effectively are working. Might have an odd LED out somewhere. And the other string has lots of LEDs out. So I need to look at this one now and figure out what's wrong with it. And there's going to be one of 2 things, or we could say 3 things, but we'll say 2 things. So in one case, either the controller has a fault, so that one of these thyristors or transistors is not switching, but I know that's not the case on these lights because the other 2 sets of strings are working and they're all in parallel. The other thing is a broken wire, or more likely a bad connection where the LEDs are. So when these wires go inside here to the LED, you can see corrosion here, water gets in them, they rust, their legs rot away. So the chances are what we have wrong with this is just LEDs. The way the wiring works on this is we have 5 wires in this set. So this set has 4 channels, as we saw, 4 transistors, 4 control channels, and it has 1 return channel. The return actual factor is usually the power coming in, if you like, the positive end, and the other 4 are effectively grounding it. So this one actually runs on DC. So we'll have like a 24 volt DC supply on one of these going to the LEDs, and then we'll have 4 returns. So the way these LEDs are wired up, we have a common supply rail. This is the positive end, or one end of the AC, okay? And our LEDs are connected like so. A sequence of, and there'll be usually, if it's a 24 volt, there'll be 8 of these in the chain, okay? But I'll just draw a few of them. And on ours, this is channel 1. And we have 4 channels. I'll just draw them roughly. Okay, we have channel 2, channel 3, and channel 4. Okay, and the way this switches, as I mentioned, is the microcontroller will switch this end effectively to ground, or with the thyristor to the other end of the AC. Okay, so this is like the common end, and that goes to our controller, and we have 4 of them. So you're switching this end, so this end effectively has a supply or the positive end all the time. Now to do this on ours, we need 5 wires. We need 1 here, and then we want 1, 2, 3, 4, okay? This part is inside the controller. So we have 5 wires. But this positive has to go to the next sequence. So we'll have 8 LEDs in a chain, but we've probably got 5, 10, 20 sets of 8, depends on the length of the chain of LEDs. So this positive end, as well as going to all of these, it has another connection on, which goes down to the next set. Okay, this is your next set of LEDs. And the ends of these connect back to here. And so on. Okay, so this is why there's more wires in these sets than you think there would be normally. What generally happens is the common one runs all the way down, so that's like an extra wire. And then these effectively, when you get to the end of one chain, it just goes back to the start of the next chain. So the way these work then, we know about the 4 chains on this, so we need to have a look. So we'll have 1, 2, 3, 4, that's the first 4 LEDs, and this one isn't lit. So we can see that that channel isn't actually working on this strip, okay, 1, 2, 3, 4. So we can see that on this sequence, we have 1 channel out, 1 string, 4, okay, 1, 2, 3, 4, yeah, 1, 2, 3, 4. So this is the first one on this chain that isn't working. Now you'll see we have 1 wire coming in and we have 2 wires going out, okay? The reason the 2 wires going out is what I've just explained. So one of the 2 wires going out will go to the next LED on this chain, which is here. Okay, and the other one will go down to the first LED on the next set of 8 on this channel. So you can see this one only has 1 going out, okay? And if we keep following down this chain, we'll see this one has 1 going out. That's the 3rd one. Again, the 4th one is here. So it's buried in there, but there'll be only 1 going out. Here's the 5th one. And we can see 1 going out again. Okay, we can follow the chain down. There's the 6th one. And there's a dim one. You see it there? That one. So that's dim. I suspect the one that's lit up dim is probably the faulty one, and probably the one that's stopping the whole set on that want that set working. Okay, so what this is a matter of doing is finding either a dim one, or if you can't find a dim one, you just have to work your way along. I'll just show you that. So to do this, you need a multimeter with some spiky probes that you can actually stick into the wires. That's the way to normally do it, the easiest way. You can use a multimeter or anything else that's capable of lighting the LED up. So we can see here that this one isn't working, okay? So we'll switch it off. We'll take our multimeter onto diode range. Let's see if this multimeter will light these white LEDs. To test if it will, I'm just going to light up one of the ones I know is working. I don't usually use the multimeter, I use something else I'm going to show you in a minute, but we'll just see if the multimeter can actually do this job. Okay, so here's one of the good LEDs. Let's have a look. So I'm going to stick the probe into the wire, and the same on the other end. I'm not sure the polarity, we'll have to figure it out. I'll put the meter onto diode range, of course. Let's have a look. Well, that's not reading anything and not lighting up. Let's go the other way. And that's lighting up, you can see it there, it's lit up, so we know that's a good one. We also know the negative is on the one coming down the chain, so we know the polarity now, okay? So 1, 2, 3, this is the one that didn't work. Yeah, so we do the same again. Coming in. Going out. Okay. And I don't have anything on that one. Now, I might have a bad connection. It's a bit awkward with this. Why is some is easier than other? But I don't have. So now we need to look at this LED. Normally speaking, you'll find one LED taking a whole group of 8 out. I've not repaired these sets before, so whether we have some more problems where we have a whole set in a chain not working, I'm not sure. So let's have a look. So we need to get inside this. Sharp knife is what you need for this job. And generally, once you split this plastic, it will kind of peel off. Okay. Yeah, so it's peeling back now. Coming off. Well, we can see this as the resistor, and I mentioned, you can see the resistor there. Okay, and this is even worse. Usually there's just one layer of plastic, this has 2 layers of plastic. And we need to get into this one. Just slice it a little bit. That one's actually thinner than the other one. Okay, we're getting into it now. Just peel the plastic off it. Right. So there we are. We have like a little bit of plastic as goes in between. So if you just keep hold of this, fix the LED if it needs fixing, and then just put the A little bit of plastic back on. So this one we can see there's the LED. Let's have a look. I'm thinking now the reason this wouldn't work as a resistor in series with it. Let's have a look. Well, this one actually is lighting, and I suspect the reason it wouldn't light up before was this resistor. In fact, it does light up, it's just very dim, you probably can't see it. So what I normally use is not the multimeter at all. I normally use this, so this is a backlight tester, but you can set it to 1 milliamp, okay? And then it gives a maximum of about 20 volts out. And because of constant current sources, it's just perfect for testing LEDs. So you can see 21.7 volts. We go to our LED that we're trying to test. Because it's on this voltage, it won't give you a shock, by the way. It would if it was on the full voltage. If it was on the 30 milliamps, it gives you a nasty zap, this thing. And this lights the LED brightly, even with the resistor. So this is why I would use this to test the LEDs. Also, if you're using this, you don't have to test every LED individually. You can split the chain in half. So we can test a number of LEDs at the same time, and this makes it much quicker. So there's the first LED, which you know is actually good. And we can just follow the chain down. So this is the second one. This is the fourth one. So if we test from the first LED to here, okay, this will tell us if the problem is somewhere in between. So we're looking at that one. And we'll go to the first one. So the first one we know coming in here is good. And we can now go to that fourth one. So we can find the wire coming into the fourth one. Okay, and if we test from the first one, if it lights up, all the ones in between should light up. Let's have a look. Well, I thought I had it and I don't have it. Maybe I have a bad connection. Let's have a look. Well, we can see that it doesn't work, so we know that the fault is somewhere in between the two. And this is the way to test these a number of LEDs at once. It's much quicker. So we'll go to the second LED in the chain now. Let's just test these two together and see if this is working. So what we need to do is we need to connect from the black wire on here, and we can go to the output from the second LED here. Do they both light up? Well, the first one lights up, but the second one doesn't, and yet I'm measuring through that one, so that appears to be a faulty LED. So down to that fourth one again, which was down here. Doesn't work at all. So we can see the second LED has a problem. In, out is fine. Into here. First one lights, second one doesn't light. So this is a faulty LED. Okay, let's look at it. So in, out, now coming through the resistor, that's fine. In here to here, this lights up, other side of this one, So that one is actually 40. Okay, and it's reading like 6 volts or something. So this is dropping quite a bit of voltage, but not lighting up. Look, on its own, it's dropping, well, almost open circuit. So that LED is faulty. Yeah, you can see which way round it goes. Well, it has like a big hoof here and a narrow one there. So let's see if we got some of these. Yeah, I have one here. So I'll change this one and then let's see what happens. I tend to mix these wires up if I'm not careful what I'm doing. So what I'm going to do is I'm going to unsolder one. That was like the big hoof end of it. I'm going to solder the other one on first, this end, and then I'll do the other wire afterwards. Okay, and I can't mix them up. If you do mix them up, you'll just confuse yourself a bit and eventually you'll figure it out after you've wasted some time. Yeah, so guys, this is the way I found the best way. Okay, so we can see now, coming down the first one, out on the second one, they both light up. Now, we might have fixed that chain, or we might just have to work using exactly the same method down the chain. We can have a look. If we're lucky, then just one LED in that little group was not working. So we'll just power this thing back up and let's see. And we can see that this sequence now are all lighting up. So that one faulty LED in there was causing the problem. And now we just work down the other groups of 8, sets of 4 of 8, and just find the problem. So you'll probably find that it's just one LED faulty in each group, and then they actually work. So as you can see, you can have one LED on the set of 8 and it'll stop them all from working. That's what I had on that chain. So you haven't got to replace all the LEDs that are not lit. Just use this technique whereby you can actually test 4 at a time, as I was doing, split it into 4, split it into 2. Something like the backlight tester is perfect for that. Or you can make yourself something using a bench power supply, 30 volts output, something like an LM317, make yourself a little constant current source. For a few milliamps, you can do it that way. Don't rely on your bench power supply constant current, because the output capacitors will discharge into the LEDs when you connect the probes and burn them out. Okay, so don't do that, but a constant current source, something like this, is ideal. And then you can fairly quickly work your way along these just by splitting them half, a quarter, and you can soon work out where the faulty LED is and replace it. So it's not as time consuming as you might think. I'll have these all working, but I won't make you sit and watch me do them all. And what else can we say other than Merry Christmas, guys? See you all soon on another Learning Electronics Repair video.